Okay, welcome to this video. In this video, we're going to be designing the main circuit. So the main circuit actually is where we are going to put all our components together. By the components, I mean the ones we made ourselves and some of the components from Logism. So let's start off by just talking about it a bit. The main circuit has an internal address bus, an external address bus, internal and external data buses also. The purposes of these are to help abstract the flow of data. So if you want to get data from the internal part of things, that's the registers, the counters, all that, to let's say your RAM, which is external, you'd have a way of doing things. Alright. It helps to make things easier and also easier to debug. So so let's begin by just demarcating some buses. So let's have our internal address bus. So we have a tunnel. Let me zoom in a bit. Okay, let's have that facing east, and this will be our internal address bus. And let's just extend that. And then let's have another tunnel face this north. Let me move that here. And this is going to be our internal data bus. So the internal address bus stores addresses, well, not stores, it's just a bus. It helps to move data, address data between components. And the internal data bus moves data between components. So for the address bus, we're going to have a program counter connected to the address bus. So let's get our counters. And for the counter, we are going to have, this is going to be controlled. So we are going to have a whole lot of control signals controlling every component. This is 8 bits. Now this is 8 bits because our address width is 8 bits. So it only makes sense for anything address related to be 8 bits. Okay. Yeah, now we are going to have a whole lot of red lines throughout, but by the end of this video we are going to have no red lines. Alright, remember, red lines are not good. Red lines may have conflicting data. So yeah, so we also need a clock, very important. So let me patch this to a long way away, and let me also, okay, let me just leave that there. So let's have our clock connected, and now you need an enable. So tunnel east, this is a program count enable. So the enable is what tells the program counter to count or load or whatever the case may be. And for the load, we are going to have program counter load. And for the up or down, whether it counts up or down, we will use that, just not yet. So let's not think about it. And we are going to connect this here. Okay, we need a control here. So that's, You know what? This is our program counter output enable. Okay, I think this is it for the program counter for now. Now we need to move on to our temporary address register. So let's drag a register. So we get a register from the top here. Okay, and this is the temporary address register. It stores addresses from it gets its data from the internal data bus. So I believe this is our internal data bus. This should be 16 bits. Okay, so we want our addresses to be from here. Where that's in. And we have conflicting. Okay, let me label this. The reason we have a conflict here is we are getting 16-bit data, pushing it into an 8-bit address. So what I'll do is I'll cut this, and I'm going to look for a bit select. Bit select. Let's see what that be. Okay, there we go. So a bit selector, it's going to get all 8. I mean all 16, and it's going to give out 8, meaning it's going to give out half. And so we are going to get a constant. The value of this constant is, in this case, since we are pushing out half, it's telling us which half to push out. And since we are looking for the 8 LSB, it means we are pushing out the half, the right half. So that's 0. So now our temporary address, oh, why do I call this a bus? This is not a bus. This is a register. Our temporary address register pushes its output onto the address bus, the internal address bus. So we are going to control that also. Okay, there we go. And this is 8 bits. There we go. And we are going to tunnel that. And the tunnel for this is going to be called TAR, also to enable. We're also going to need a tunnel for our TR right enable, and then our clock. Alright. Okay, so our clock, yeah, so let's clock that in. Then tunnel, said we're going to have a tunnel for our right enable. So that's TAR right enable. Okay, let me make that face east. Okay, and I think that's it for our temporary address register. So now we can move on to our immediate value register. So we get another register, drop it. And this register, let me label that immediate value register. Okay. This register gets its data from the instruction directly. So it stores the immediate value segments of the instruction. So we are going to tunnel in our instruction. Oh, wait, this has to be 8. The instruction has to be 16. And since we are trying to push 16 into 8, we'd need to select some. So we take a selector, data bits, it takes in 16, it pushes out 8. And which are we selecting? We would want to select, it's similar to the temporary address register, we are going to be selecting the first half. Okay, for immediate value, we are going to need a write enable, and we are also going to need a clock. So let me plug that in. And I write enable. So when do we write enable to the immediate value register? Well, every time we get an instruction. And when do we get an instruction? When the program counter increments. So our tunnel, our control signal is going to be the program counter count enable, because the only time we would want to update the contents of this register is when we get a new instruction. And where does it push its data out to? It pushes it to the internal data bus. Since it's pushing out 8 bits onto a 16-bit bus, we are going to need a bit extender to extend our 8 bits to 16 bits. And we are going to control that also. Everything needs control. So that's 16 bits. Okay. So this, we are going to have an immediate value output enable for that. Okay. So now we are pretty much done with the immediate value register. Let's move on to the general purpose registers. So let's drag GPR out here, D out over here, DN, where is DN from? DN is going to be also from the data bus. I'll select WEOE clock in. Okay, for these, let me patch the clock first. Now I'll select, I'm going to take a tunnel, pointer east. It's going to be 4 bits because we have 16, and that's GPL SEL. And I'm going to have another tunnel for GPL WE, and I'm going to have another tunnel for GPL OE. Oh wait, what did I just do? Okay, so yeah, let's connect them appropriately. GPL SEL to register select, GPL WE to write enable, and GPR OE there. GPR OE and GPR WE should be 1 bit each. Oh yeah, and okay, so I think that should be it for GPR. Let's move on to the ALU. So with the ALU, let's drop our status flags. Our flags get data from the ALU, so we drop our ALU. and I would suggest you align the data so it's easier to connect them. So carry in, 0 in, negative in, and we also need to clock this. There we go. Okay, so for our ALU, we are going to need about 4 control signals. Okay, so this is going to be our ALU opcode. Then we are going to need one for ALU output enable. Our output enable would go to data bus. Then we are going to need one for ALU write enable. And then, okay, I think that will be it for now. So the opcode goes in here. Output enable, and then write enable. Let me move this down a step. And so opcode wants to be 3 bits, so let's make it 3 bits. There we go. Now ALU takes 2 inputs. These inputs are going to be from registers, so we are going to have 2 registers. I'm going to call this R1 and I'm going to call this R2. Okay, so for 2 into input 2, and these are 16-bit registers, so let's change that. Both of them should be 16, not 17, 16. Okay, and both of them are going to need clocks, so patch them in. Okay, and where do they get their data from? Well, no other place than the internal data bus. So let's go up, arc that connects that. Let's see. Okay, so now we need write enables for both of them, so you know to do get tunnels east. This is R1 write enable. There we go. Plug it in. We're going to have an R2 write enable. Pointer east. Go ahead and plug it in. Okay, so now we are going to need a write enable for our flags. Let me shape that a bit more. Yeah, so let's just tunnel that as usual. I'll call this set flags SF. So we go east. Okay. Alright. So we have to connect R1's data. Okay, there we go. Remember, by the end of this video, we would want to have no conflicting data. The reason we're having conflicting data is the components are all doing whatever they want, but we would control that. Okay, so Now let's move on to, well, you add a probe to our stored result just to enable us see the result in a base of our choice. So let's just add a probe. Let's have that in signed decimal. Yeah. So whatever the result is here, we can see it in decimal here. Okay. So let's move to the other half of things. So over here we have to get our external address bus and our external data bus. So channel point at south. I'm going to call this external address bus. And I'm just going to draw a line. And then I'm going to duplicate that. Wait, I didn't even have to duplicate that. And this is going to be external data bus. Let me just align them for the fun of it. Okay, so the bridge between our internal and external address buses, we have a register there. That register is our memory address register. The memory address register is the only way to communicate or to send an address from the internal bus to the external. So its data is going to be whatever is from here, and it's going to need a write enable, and it will also need an output enable. Okay, so we have a tunnel eastward. So this is MAL write enable, and yeah, so I said we're also going to need an output enable, so let's get our buffer. Should be 8 bits for the buffer. Our external address bus should also be 8 bits, and our external data bus should be 16 bits. And over here we're going to get a tunnel for our control line here. This will be MAR output enable. Pretty simple. Okay, not. And so where is this data going? This data is going to go to our RAM component. So let's go to memory, pick out RAM. So our RAM is going to, first of all, we have to edit it. So this is 256 by 8, but we want 256 by 16 because we are storing 16 bits data in each location. And we don't want byte enables, we want line enables. Okay. So this would go in here. I think we can drop this up. And we are going to need a RAM write enable. So let's go to our tunnel, face that east. Label is going to be RAM write enable. And we are going to need a clock. So let's just patch a clock in there. Or let me patch the clock upward instead. Okay. Um. Well, let me bring this. Yeah, just to create some space. So now we are going to want to connect over here. This is input data. Okay. And so the input data comes from our memory buffer register. So we are going to work on that. Okay, you know what, let me just take this back up here. Okay. So we get another register. This is going to be called memory buffer register. So our memory buffer register is going to have its data output connected here, right? So let's, but it's not going to be connected directly there. We are going to have to control it, with write enables and output enables, the usual. Let me extend this up. Just there. But the memory buffer register is a bit unique because we are not only storing data into it, but we are also getting data out of it both ways. So it could be from internal to external, or it could be from external to internal. So we are going to have to cater for all of that. Um, okay, so first off, let's give it a clock. Always need a clock. Now for the input, and also this is supposed to be a 16-bit register because we are storing data in there. For the input, we are going to connect this. Okay, and we are also going to get input from here. So for that, we would need to control that. Get a controlled buffer. Oh, undo that. Our controlled buffer should be 16 bits in width, and the name of its control signal would be mbr underscore. This is from internal, so in underscore write enable. We are also going to have a tunnel for mbr write enable face that east. We are also going to need tunnels for the outputs to wherever we want. So Let's have a controlled buffer here, here. This is going to be a 16-bit buffer, and the name of its control signal would be, so this is to the external data bus. So that would be mbr underscore external underscore output enable. Let's have that point east. And remember, we would also want to have data from here onto our internal data bus once again. So let me just pick that. And as usual, we are going to need to control it. So another control buffer. This is going to face west. Sixteen bits. There we go. And once we have a buffer, we would need a control signal. This control signal is mbr internal output enable. Let's have that facing south and plug it in. Okay. So now our mbr is properly wired up. Let's finish up with the RAM. So our RAM gives us output. We get output here. We need to control the output. Controlled buffer west. Slot that in. Our buffer should be 16 bits and it should go to the external data bus. And we are going to have a control signal. This will be RAM output enable. Let's have that facing south. Alright. So now that that's done, we are going to, let's see, I think that's pretty much it. Oh yeah, one thing, we need to get the instruction. So we need to create a tunnel, face that east, and this is instruction. And remember, with tunnels, when two tunnels have the same name, what that means is they are working with the same data. So they have to conform in all senses. So this should be 16 bits. There we go. So now our instruction is taken from here. Instruction comes here. Cool. So let's take a look. Okay, this doesn't have to be solo. Have we missed anything? Everything looks connected. As we go along, we'll see if that's actually the case. So I think we can get to our control signals now. So what we're going to do is for every tunnel we've created, we are going to have it down here to enable us to manually control our CPU. So tunnel input and control CV. Now we are going to have a lot of these, so I'm just going to duplicate it a few times. Okay, so let's start with the program counter. For a program counter, we have PC load, PCEN, and PCOE. So here we have PC load, PCEN, PCOE. Then after that, let's move to the temporary address register. So we have TARWE, TAROE. Is that it? Yeah, that's it. So let's move to immediate value. Immediate value has only one, IMOE. So I think I'll just put that here. Let's move to the ALU. The ALU, we have R1, R2, and so many others. So I'm going to have R1 WE, R2 WE, ALU WE, ALU OE, ALU OPC. OPC is expected to be 3 bits, so we make that 3, and we also have to make the input 3 bits. And then we have SF to set the flags. Okay, so the ALU is pretty much done. Now we are going to want to move on to the GPR. So GPR, we have GPR SEL. SEL is expected to be 4 bits with a 4-bit input. Then we have GPR WE. And we have GPR OE. Okay, so now let's move to this side of things. Over here we have MARWE, MAROE, RAMWE, RAMOE. So let's do those. MARWE, MAROE, RAMWE, and RAMOE. And we still need more. We need 4 more. Okay, so let me duplicate this. Let's just bring that down here. So that's going to be MBRWE, MBRINWE, MBRINOE, and MBREXOE. Let's separate these a bit. Okay. Now, to be certain that we are actually done with all our control signals, go to simulate and reset simulation. If there are any red lines anywhere, it means we are not done. So let's zoom out and see. Well, it appears we are done. So if you followed everything exactly, you should have no red lines. If you have any red lines anywhere, there's an issue somewhere and you'd have to check that. I'm going to leave the file up to this point in the description. So in case you have any issues, you can also just download that and compare. Alright, thank you for watching. In our next video, we are going to be testing our CPU.